Hello, everybody. I'll wait 1 minute before we start, and then we can dive into the topic circular economy of plastics and our NETZSCH tools. Okay, hello, everybody. Welcome, and thank you for joining today's webinar on circular economy of plastics, NETZSCH tools to identify and analyze unknown compositions. My name is Natalie Rudolph, and I'm the Business Field Manager Polymer here at NETZSCH Analyzing and Testing. I have a background in polymer research in academia and in industry, and I have a special heart for this topic. I co-authored a textbook on the topic of understanding plastics recycling because not only do I think it's important for us at NETZSCH to support it, but for all of us to think in that regard and work in that direction. So when we think of circular economy of plastics, we know we have to reuse and recycle as much as we can. And the typical circle that we have should be manufacturing, consumption, recycling. And we really have resources in and waste out. And today I wanted to actually start looking at what kind of waste do we have, because that is important for the analysis and the different types of recycling. So I took this graph from a kind of recent publication from some of my former colleagues at the University of Wisconsin-Madison. It's a review, 100 pages, dealing with the current state of recycling and focusing a lot on chemical recycling, which we won't talk in detail about today. But you can see at the very top really what all goes into a materials recovery facility and what you can do with it. So if we take a closer look at the upper part, plastics really play a role in the post-industrial plastic waste. It can come from ocean plastic waste, from flexible plastics and films. Textiles has a huge portion of synthetic or polymer fibers. And then we can have post-consumer plastic waste and municipal solid waste. And what I like about this graphic is really that it gives us an idea what value we can still put on what's coming out of an MRF. So when we now look at that, we have post-industrial plastic waste, or pre-consumer waste that it's very often called, which is in majority that's production scrap. And that means we normally have a single type of material and or known composition. We know what goes into those products. But we can also have off-grade material during production, an incorrect batch, or transition batches in compounding or even polymerization. And then we can look down here that also the flexible plastic films and textiles have that to a degree. We have the post-consumer plastic waste, single-stream recycling, dual-stream recycling. Municipal solid waste can also have some plastic still in it, and obviously ocean plastic waste, which we have heard about a lot more in the last couple of years. And so they're really distinct differences. As you probably know, our pre-consumer waste is relatively clean, and we know what it is, and it's not mixed in general. And post-consumer plastic waste is really everything collected, and we have to sort it. And so when we think of that, when we look at the lower portion, what we really need to do is we need to sort and recycle the plastics. And the way that we have done since the conception of recycling is mechanical recycling, and grinding it and extruding it, and then we think of it as resins with degraded properties that we can resell, or we use it as additives, for example, in asphalt, or the slightly newer research arm, let's say, I mean, new means still 20 years of chemical recycling, where we see more and more work being done, where we then get pure resins with virgin properties. And so today we're still focusing mostly on just the different materials and where they come from, and why there is a certain need for thermal analysis tools to identify and analyze, since we know that the typical analysis tools like Fourier transfer, infrared cannot help with all of the plastic that we have. And as you probably know, it affects us all across the globe. We produce plastics everywhere, and we produce parts out of plastics everywhere in the world. And when we look at what types of resins we're using, I want to have you pay attention to the right side of this chart, where you see all the polyolefins, the PP, the LDPE, and HDPE, and they really make up 50% of the material that we're using, the plastic materials that we're using. And most of that, so now we have to look down here, we have the polyolefins. They're mostly going into packaging, a little bit building, automotive, and then all the others. But the big majority of it comes from packaging, so films and maybe bottles, but mostly thin products. That gives us an indication that we might be able to distinguish them just by the delivery form. And when we look at the different sectors like packaging, electrical, electronics, and automotive, I just took these out. You can find that that's an analysis we did in our book. The most common polymers that are used in packaging for bottles are PET, as we all know, then HDPE, a little bit of polypropylene, LDPE, and PVC. For films, the majority is LDPE, 20% PP. So we see that what kind of materials we have, and that we have relatively big portions of them. For electrical, electronics, and automotive, we didn't get proportions at the time. So it's just that there are, in most industries, we focus on a smaller group of plastic materials, but as we know, they can have a variety of additives, molecular weight ranges that all have an impact on how they're processing and what their properties are. But really, especially looking at packaging, to drive that home, polyolefins have all the same chemical structure. It's just CH, and they can only be differentiated by their melting temperatures, and unfortunately not by their IR spectra. So therefore, we believe that DSC is needed somewhere in the reprocessing of 50% of plastics production or the plastic waste. And that's why I'm going to talk about that. So how can DSC be used as an identification tool? I'll do just a really quick recap, because I assume most of you have an idea, and we have other webinars that focus really on the DSC method. But differential scanning colorimetry, short DSC, is a technique in which the heat flow difference into a substance, here on the right labeled as sample, and a reference material, which is in our case an empty crucible, is measured as a function of temperature, while the substance and reference material are subjected to a controlled temperature program. That's called a heat flux DSC. And the actual signal at the sensors that we get is we can record in red the temperature of the furnace, we get in blue the reference, and we get the sample in green. And when we see a deviation between reference and sample, we know something has happened in the material. And depending on if we have energy going in or an endothermic or coming out, an exothermic process, that refers to different effects. And this is just a general overview, and then we'll really dive deeper into the topic. Endothermic effects, the melting can be used for identification of materials. Blends has always been a thing to use. It can be used to measure enthalpy, determining processing temperatures, glass transition, evaporation, what solvents are released, and to a certain degree thermal degradation, but thermal gravimetric analysis is better suited for that. And exothermic processes, we can study crystallization, all kinds of aspects about it, polymerization reactions and curing reactions. So there's a lot that can be done with DSC, but again, today I want to focus on the identification aspect of it. And I also want to touch on another software tool that we have in our Proteus software. Proteus is the software family name, and that's the Identify Database Search System that can be used for material identification. It can be used for quality control, so you can set boundaries and then it can tell you right away if something passed. And it can be used for archiving, searching, and finding, or data mining in general. And the first and the last is what we're going to talk about today when we talk about the Identify database. So I said polyolefins, we have 50% in the materials that are produced, and we have quite a variety of polyolefins. And as you can see, I picked each a representative of each of the different polyolefins that we have, and you can see that the melting peaks are different in the peak temperature where that happens, and definitely in the enthalpy. And depending on the combination, I also put PP in here, you see that we have a distinct difference, definitely in the melting peak, but we also have overlaps, and that's important for the topic today. And that is really related to the structure. I just put this as some samples, but as I said, it's really only CH that's in the material, so the melting temperatures are important for identification. And then when we think of enthalpies that we really want to quantify the materials, we typically look at the enthalpy. And so I wanted to give you an idea how wide the range of enthalpies can be within one product family. And so in Identify, we have a huge database of more than 1,100 plastic grades. We call it the KMW database. And that's real grades that you can buy on the market. And I just looked at all the LDPE grades we have in there. And so the melting enthalpies range from 108 to 131. You can see the graph of all these overlapping here, and I'm not showing a graph for HDPE, but I can tell you the values. The enthalpies that of the materials we have in the database range from 155 to 237, and that's a huge variation that makes it really important to know the reference you're referring to if you really want to know the weight percentages to a certain accuracy. I'll talk later about that. I just wanted to have that as a context for everybody, that variations are huge. The study we did initially was of mixtures of LDPE and PP. I'm just going to turn off my mic real quick and start it again, because some people seem to not be able to hear me anymore. I hope that's better. Give me a sign if it's still not possible, and I'll keep an eye. And but I'll continue with the webinar otherwise. Okay, so we looked at mixtures of LDPE and PP, and I picked one ratio that is could be quite quite typical. Okay, thanks for the feedback. You see here in light blue the first heating, two distinct peaks, first for LDPE, then for PP. You see the crystallization curve, and then we see the second heating in blue. The second heating is normally what we look at because we're interested in the material property and not in the processing history. So for LDP and PP, it's a more simple example because we see two distinct melting peaks. We see a slight shift of peak temperatures to lower values from first to second heating. And the crystallization curve that you see here, as we're cooling, PP is crystallizing first, and then right away LDPE is starting. So that's a good indication, and we know that from other researchers, that there is some interaction. PP is acting as a nucleus or nuclei for LDPE, so the crystallization is slightly affected, which has an effect on melting behavior and crystallinity compared to just the neat materials. So when we enlarge the blue curve, and we just want to understand the enthalpy that we have with 80% LDP and 20% PP, we get an area of 106.7 joule per gram. And since these peaks are so easily distinguishable, we could easily just use the function of partial areas, which allows us to separate the area of the two more or less manually. So we click on partial areas function, set the cursor for the upper and lower limit, so that would be here and here, and then we set the cursor at the end of the first peak, and then it calculates us the percentage that the first peak contributes to the whole area, and then we set the cursor at the upper limit, and then it gives us, this is now 100%, so we know that roughly 17% is 17% is PP. But overall, it's much better, especially if you want to identify materials, if you use another functionality that's called peak separation, and you find it in the menu evaluation. And I just enlarged what you can actually do here. This is the picture you would see. And in order to perform peak separation, you can select the baseline type, select the peak shape, or have an automatic peak search or manual search operation. But you can also still define shape, height, width, asymmetry, and then you can get a solution. You'll always see how good the fit is up here, and I'll show you later the results that we obtained with the materials we looked at. And then you get the following view. What you see here is we picked automatic selection of peak shape, general shape. We got a very good agreement. And in blue, you see the actual measured curve. In red, you see the fit that was performed. You see with PP, it's not as ideal. And you can do that by changing the number of peaks, things that you do. That's there is some expertise in it, and we have other webinars and even a YouTube video that you can check out if you're interested in all the details on peak separation. But what is very important is that you get the percentages of enthalpy, and you get two separate curves. So it calculates us one LDPE curve in green, and it calculates us one PP curve in magenta. So we have now two separate curves. And this is important. It gives us three advantages. The peak area can be used to compute the weight percentages if the base materials are known. So if we know the LDPE and the PP. And now let's see how we can look that. We have a concentration feature that we originally created for impurities in metals. So you have to tinker a little bit with it to get what you want. Sorry, I'll start with how you would manually calculate it. And so we have to look down here. Sorry, that sounds better. So we know the enthalpy of the pure material for LDPE and PP. We know the areas of the separated peaks because we know the percentages and can calculate that. And then we can calculate the concentration, which is the weight percentage, so 77.32 and 16.42. And that gives us milligrams if we wanted to compute it, because we know the total weight of the sample. And we can also do that automatically in this concentration feature. Now I go up here. And in order to be able to do that automatically, you have to create a library with enthalpies of the pure materials. So that would be the 101.2, which I selected here for the PP. And then I choose the area of melting, which is also the PP peak. And I just click on calculate, and I get exactly the same weight percentage that I calculated by looking up what weight my sample had and stuff like that. So the software can do it automatically, but only in regard to a reference material. And that's the crux of all of it at some point. For this study, we had it, and I think it's a discussion we should have of how can we maybe create libraries like that to have a good idea and be accurate in predicting the weight percentages accurately. So this is the first advantage that we have, that we can compute the weight. And the other advantage is that the two curves can be separately analyzed afterwards. So we can, for example, analyze the peak temperatures, but we can separately use them in this identify database. And so identification is possible, which wouldn't be correct for the compound curve. And I show that to you here. For a curve like this, even identify is more or less able to identify the two materials, but if you have overlapping peaks, it's very important that you have them separated. And if we had the two curves, you see the agreement or similarity, as we call it, with LDPE is relatively low. Now we have the separated curves, only the LDPE curve, and we have a really good agreement with our LDPE in the database, and the same for PP. We get a high similarity with the PP that we have in the database, and that's in the database. You can use it, and there's an additional database with, as I said, the 1,100 plastics, and it's growing. And it's important for the analysis that we use in the comparison. We use qualitative parameters because that doesn't compare enthalpies. Otherwise, the similarity might not be correct, because we have a mixture. So the enthalpy per sample weight is skewed. So let's talk a little bit more about the archiving and searching using identify. Searching, we just seen. But the archiving is interesting when we think of recurring materials that we have. Either it's a research study or it's material that you get constantly from the same supplier. There might be some possibility to create calibration curves. And I show here what we did for the LDP and PP, the whole study where I showed you the 20/80 ratio that I had all the examples for. When we do that in 10% steps, we get, for the LDPE, we get melting enthalpy curve as a function of a mixing ratio, and for the PP, we get a curve. And the different slope of these curves already indicate that we have different enthalpy and crystallinity of both materials. And then what we did, we created unknown mixtures. Obviously, we knew, and we just wanted to create something that didn't fall didn't represent something we did before. So we picked 1585 and 75/25 ratio of LDPE to PP, and you can see that the green dots that represent that fit really well on this calibration curve. So a calibration curve like that is one of the only possibilities to obtain weight percentages when you have pure material. And not only can you plot this like this, but you can also generate your own database. So you could make your calibration measurements, and then you save the different mixtures with a nomenclature that works for you. So for example, PE70, PP30, PE80, PP20, that always gives the ratio. And then when we have the curve of the 75-25 ratio, we get a very high similarity with the 70-30 and 80-20. So really the boundary mixtures that we have in the database. And the same work really well for the ratio of 15-85. So you can get quite accurate results based on the step widths. Here, 10%. We pick 10%, and the variation of the actual PP and LDPE grades. And with that, what I mean is that depending on what you use material for, if you're creating an injection molding part or a film, your molecular weight and the branching of your material will be different, or the injection molding grades have more in common than the film blowing grades. And so there is some similarity if you know that your material is coming out a waste collection of flexible film versus other plastic streams, or if it's bottles, for example. You can narrow down the grades and the behavior that you have. And so conclusions that I want to leave you with is that the DSC method can be used for the characterization and separation of recycled material in single and mixed waste streams. We're currently working on a study that I hope we can show you soon, but we have good indication that we can detect quantities as low as 1% in a mixture with our DSCs, and especially with our newest DSC 300 calories. And we have fully automated curve evaluation and material identification by means of database comparison, which makes the differentiation of the recycled materials easy. When the base material is known, or the properties are known, like the enthalpy, the material proportions can be calculated, but the error depends strongly on the known enthalpy. There's a couple of caveats. The sample weight that we're using is small. With an auto sampler, you can cover that and still get a lot of measurements done overnight. But the number of samples and statistical significance for your case, if you work in a big bale or if you work in research, I mean, that's very different cases. That maybe your questions will give me an idea of what you're most interested in. That needs to be evaluated for each case. Multiple components with more than 2 overlapping peaks obviously increase the complexity. We're currently working on a study where peaks are more overlapping. Here's an example and an outlook for you to see a mixture of HTP and PP. And we're working on more, but we're not done. So stay tuned in the future for more information. But we picked a similar ratio here, 20% HTP and 80% PP. And here you already see the peak separated curves. What we did here is we actually did a mathematical trick to get a better fit of our to the curve by telling the peak separation tool to use 4 peaks rather than 2. That's really just a mathematical feature. But as long as these smaller peaks, or the peaks are within one larger peak, this is a valid thing to do. And we can only use the HDPE peak to calculate that percentage. So we have a bigger overlap than in the LDPE mixture. You see, we're not going back to the baseline. The multiple peaks can be used to improve the fit. And we only use this HDPE peak to calculate the concentration for both components. In this case, we knew the specific enthalpy of the pure HDPE was 220.9 joule per gram. And we know the area of our compound curve, and so we get 20 weight%, which is a really good agreement. And obviously, you might not ever get it that great in real life if you're not preparing mixtures, but it's a really good agreement. And we're working with researchers at the University of Ghent and Maastricht, and there's also a lot of publications that are going to come out in the next couple of months. And they are focusing on mixing ratios that are more on the boundaries or the edges, where we have very small concentrations of contaminating plastic, and they're looking at techniques to also identify them, for example, with DSC as one of their main tools. With that, I'm would like to go into the Q&A session. I, however, still want to point out, if you think about it later today or tomorrow, the next couple of days, and you have questions that you didn't think of right now, obviously you can find me and contact me on LinkedIn, but you can also email webinar_ngb@netzsch.com. If you note this email address, you can ask me questions later on. And last but not least, a little bit of advertising. We're at the K-Show next week, or the week starting next week, and I will be there. Other experts will be there. If you have specific questions that you don't want to ask in this big group, but you would like to talk to someone in person, come visit us at the K-Show, Hall 11, booth I-79. We're happy to meet you and discuss all your needs. And now I'm going to take a look at the question. Okay, I have a question. Can we separate LDPE, HDPE, and LLDPE from the matrix? I'm not 100% sure what the matrix means, but I'm going back to one of the very first slides here. So you can see LDPE, LLDPE, and HDPE. So HDPE and the LDPEs is possible in a lot of cases. I picked these randomly out of our database. There might definitely be grades where the molecular weight of HDP is a little lower, so this peak would be shifted in this direction, or of the LDPEs is a little higher. We have problems with the overlap of LDP and LLDPE because we very likely would underestimate the LLDPE. You see, the LLDPE often has this bimodal distribution, has two peaks because of the branches that we're picking up. And if we do peak separation and we don't know that it's LLDPE and we can tell it that the shape should be similar to this, we would very likely create a new peak separated curve that looks like this green one and goes down here, and you see we would underestimate the enthalpy based on that. So LLDPE and LDPE are really tricky ones to separate, but it depends on your individual sample, and it's definitely worthwhile to check it out. There's also LLDPE in the database, or you can create your own database. That's maybe a point that I should mention. I showed that you can create that for mixtures, but whatever you measure in your lab, you can store it in the identified database and use it as reference later. So that's something you can definitely do. Let me slow down. So, and then on slide 22, the question is, slide 22, how to determine the onset of PE melting? So, with peak separation, and maybe there is a problem with the slide. In peak separation, I really only need to set the bound. So you as a user need to set the boundaries of the really lower and upper limit, and the software is performing tangential fits to determine where the baseline is and where we start deviating, where actually this peak is starting. And you asked about the PE melting. So PE is here, the LDPE. So we would go really far to the lower region. I can tell you exactly what we used here. Yeah, we started at 35 degrees C. But if you actually are referring to slide 21, I'm just assuming that that could be a typo, or that you didn't read the slide number properly. Here, I actually really just look where the if I do the partial areas, you determine visually where the previous peak touches the baseline, and this is where you set the end, and then the rest is already contributing to the PP. Okay, then there is a comment. I find that maybe I'll go to this. I find that the melting crystallization peak shapes tend to depend on sample size. Is it important to control sample size for good curve fitting? Maybe that would be really a question to contact me afterwards directly, or visit us at the show. If you have really good contact of your sample with the bottom of your crucible, the sample size shouldn't have an effect on your peak shape. That if it's packed, and if the heat transfer into the sample is really working as it should, it should look similar. But I'm not quite sure if that captures the effect that you're referring to. So maybe we can connect later. Then the next question is, what if some of the components in the blend do not have a melting temperature, or some of them are in very small amounts as additives? Yeah, okay, so I'll have a melting temperature. Obviously, that would be a glass transition. In that case, it's also impossible with the DSC to quantify them, because we can really only use the enthalpy to quantify them. We only get an idea of, since glass transition shows up as a step in the curve because of a change in specific heat capacity, we can only really know a little bit from the size of the step if there's more or less material in it, but we have no means to identify. But a lot of amorphous materials and semicrystalline, you can distinguish also with FDIR. So if you're not happy with the DSC result, you should be able to see it as a step, and you should see the other materials as peaks. You might need to use other tools, but it's also not possible to quantify amorphous plastics with the DSC method. That's not possible. And then, as I said, we're working on a study to really tell you how small of a quantities we can actually estimate and detect. And at least for semicrystalline materials, the first results indicate that even 1% isn't a problem. And then with additives, again, it's important that you know what and you have a reference that you can identify the additive that you have in there. So I'm thinking if it's a flame retardant, that might be a lot more tricky than if you need to employ thermal analysis because nothing else helps. Then I would think of thermogravimetric analysis, and maybe that's a topic to discuss also in more depth in a separate setup. Yeah, but additives is also, you have to know to a certain degree what it is, otherwise it's hard to identify. Yeah, okay. And then one question is about, I talked about pure PP and polyethylene. How about the influence of fillers like glass fibers or mineral and talcum? Yeah, so if we wouldn't think about blends, then what I showed you with this concentration feature, if you can separate the material and you know what the enthalpy of, I go to somewhere where we see it better. So I have the LDPE material that has potentially a filler and in it. So the area here would be smaller than the area of an LDPE of the same weight that was without any fillers. So based on the area of your material with fillers, you can also compute the amount of material that you have in there. It's typically done like that. You normalize your measurements based on the weight percentage. And if you don't know the another way to determine the weight percentages of fillers like glass fibers and mineral or talcum, obviously, is also thermogravimetric analysis, where you can literally just burn off the organic matrix and you can obtain the weight of the mineral or inorganic additive filler or filler. Yeah. And then another question is about if the method also works for blends which mix better than PE and PP. Yeah, so you can use it for ABS, and you can use it so acrylopyral styrene, so a blend that is naturally occurring. We have some examples on our website, so contact us if you're interested in know more. It's possible to distinguish between them. Again, here it's an amorphous material, so it's a little bit more tricky, but a nylon 6 with ABS or a PET a mixture, those blends, it works, but I hope it was also clear that it has limitations. And I say that as my personal point of view is really, I think that it can be a distinguisher between companies or a competitive advantage if you learn to understand your material that well, that you can distinguish because you build a database of materials and you utilize functionalities like the identify database to actually capture all the measurement data that you generate in your labs, and you have that as reference and you can really do data mining with it. I think that that is something that might set companies apart in the future. I hope that answered it. Again, please feel free to contact me if you want more information about that. Then you mentioned that knowing your reference is important. If I always use an empty crucible, how does it impact my measurement result? That is okay. That is, I'm not 100% sure if I understand and can answer that properly. The empty crucible is a reference in the sense of it allows us to really see the effects happening in our sample. We see the deviation between, sorry, now I'm scrolling in the wrong window. You see the deviation between the sample and the reference, and you see if something exothermic happened, endothermic, and how much energy is needed. But when I refer to the reference in this talk or in this webinar, I'm talking about a reference material. So it wouldn't be an empty crucible. It would be a first measurement that you do on your LDPE without any other components in it. So the reference in the DSC is an empty crucible versus a sample. And the reference in the identification that I talked about actually refers to a reference material that allows us to get the enthalpy value to calculate the weight percentage. I hope that is a little clearer now. Okay, and then a question that we get often. What if certain additives such as UV stabilizers or fire retardants are unknown? How would that work with DSC in the Identify software? I really I know how big of a problem that is, and we haven't found a solution that's universal. It is really you have to have an idea of the UV stabilizer and or the fire retardant that you have. Otherwise, or you need a reference to identify it, either because of your knowledge or because you get it out of databases. That is slightly different to the FDIR method, where a database is part of the package, where you always want to compare this fingerprint to all the values in the database. For DSC, it's really we have a database of over 1,000 different grades of materials, but we don't have a database of all different kinds of UV stabilizers and other things. And then if they're really mixed in well and they're not really visible as a separate exothermic or endothermic effect, it's also not really possible to determine them. There is, as far as I know, there's no cheap method or affordable method to do that. And then how can we check about other types of contamination which may found in the in the waste plastic? So ideally you have at least an idea what you're dealing with. For example, if you think of metal and other contaminations, I actually think that thermochrometric analysis is better, because it's a method that we frequently use and that is set up to actually measure to very high temperatures and get all degradation effects that happen in this temperature range. And for example, as I explained with fillers, and maybe metals, you would have the metal as a residue in your pan, or you could really heat up very high and then you would detect that it's metal. With the DSC, that is not so easy, because you don't necessarily want to start degrading your material. That could have an effect on the sensors in your DSC. So you have to be more careful with that, to just heat it up to 500, 600 or 1,000, depending on the DSC you have. This could very well have an effect if degradation happens and it condensates on the sensors, things like that. Is it possible in the database of NETZSCH Identify to tag the materials based on their applications? It could be the case that melting enthalpy of, let's say, polyolefins from different applications have different average melting enthalpies. We have actually discussed this. I see, okay, it's a friend asking, one of the researchers will collaborate. In the database as we have it today, with all the plastic grades that are in there, there's no information about it. But if we think, and I think that's what you're alluding to, that is a valuable information, it could be included in the name, and then that could be searched for. But there's not a separate field that you would enter to obtain that. But it's something to think about in the future, and I think that's a very valid question, or even a comment, an idea. Okay, and someone said they missed the first part, and I actually didn't explain how we prepared the mixed plastic samples for the LDPE HDP for the LDPE PP study that I showed. Mostly, we literally just chopped pellets into smaller pieces, and really small pieces, and put the different pieces in the pan. For the HDPE PP study, where you also saw as an outlook a good agreement, here we wanted to actually really blend the material, and we performed blends on a twin screw extruder, and we worked with a company to obtain those. Then the next question is, do you foresee that it will be possible to use this technology to identify, fillers and additives that represent a very small, okay, I answered that it depends on the quantity. We're working on that, but with fillers and additives, you at least need to know what to compare it to. Can we do the same with 2 glass transition with the CP for 2 elastomers? I actually haven't tried that yet. I would have to ask colleagues who have worked potentially more with elastomers. So if you're interested in that, feel free to email us and we can follow up on that. I can't answer that at the top of my head. And can you differentiate a PP copolymer from a PP homopolymer? Not really. The distinction between them could be a little bit in the peak shape, but the deviations, as I was trying to show, are already pretty significant between grades itself. So the molecular weight definitely has more effect on the peak temperature and the shape than the copolymer and homopolymer. So I don't think that's possible. We haven't. That's just from what I've seen, not really having tried to do it. The question is if aging, like UV and seawater exposure, if that does impact the polymer crystallinity. I think that's what that means. So melting behavior in the DSC. So if the degradation really leads to chain scission and significantly lower molecular weight, then you would have a problem because your material might not appear as a PP anymore. For PP and HDPE, there might be a significant enough difference, but it really depends on the degree of degradation that has happened. That's something to look into for sure. Okay, what is the reason of peak broadening to the lower temperature ranges to the left? I'm not sure exactly what you're referring to. It could actually be on slide 17, so I'll just go with what I think the question means. So the broadening here is really that the DSC peak that we see, that is that shows us the melting of the crystalline structure. So the smaller the crystallines, the bigger the variety of in crystalline size, the broader is the peak. So I'm just taking the PP peak here, try to disregard the other curves. So this here is the melting of very small crystallites. This is the melting of crystallites that are a little bit bigger. So this is really what's happening as the material is melting. We have larger and larger crystalline structures that are melting. And so the more, like HDPE, for example, you see that that is definitely a little bit more narrower in the crystalline size than, for example, this LDPE, where you see this very broad peak and the increase. I hope that was your question. LDP and PP are not compatible. How can we analyze the compatibility of polymers? So that is actually something that we use. There are a lot of techniques, but the compatibility I like to analyze it with rheology, with rotational rheology, and I have another webinar that probably a half a year ago that's on YouTube that you could check out, where I talk about rheology study to study compatibility of, I think, LDPE and PP or HDPE and PP. So rheology and the rheological behavior is a good indication for compatibility. Yeah, I don't have any examples for other than PE and PP mixtures for amorphous material like polystyrene, but contact us and I can look at what we actually have in application notes. Or if we don't have anything, I'll take that as a sign that we should maybe create a couple of examples for you. And then you mentioned that there's variation between melting enthalpies within LDPE. If we want now to check if a mixture contains LDPE, should we check for a generic LDPE generated from all curves or compare it to all individual LDPE measurements in the reference database? So it's definitely a possibility that would be here. It's definitely possibility to generate what we call an average curve that you can look at. But I think the most interesting thing would be to just let the database look at the degree of similarity and see if it fits better to one or the other, rather than working with the compound curve or the average curve, as we're calling it. Okay, and then there's a question if we have any examples of DSC peak traces that are from an actual plastic waste stream, say from a recycler or post-consumer waste. For that, I would also like to point you to an earlier webinar that you can find on YouTube. It's also and you can always contact me and contact us if you want the link, but if you want to be quicker, you can just search on our YouTube channel. And there we actually had material from a recycler that we analyzed and used the Identify database, and we have application notes about those materials as well. If you wanted to have more details about the studies, just contact us. Okay, and then that's almost the last question, and then we're running out of time. On page 17, the question is, why is there a double peak for LLDPE and not for LDPE? So that has really to do with the branching. LLDPE had the short branches, and LDPE has the long branches, and that has an effect on the crystallization. So similar to what I pointed out earlier, it has something to do with the crystallites or spherulite size. And so this means as we're starting to melt, there's a lower amount of crystallites of that size than of this and this. And that has to do with the branching and the configuration of the material and how closely it can pack. And the crystallization behavior. So you can see that in the crystal growth and crystal growth speed. Those are all effects that you can look at also with DSC, but that's more general analysis of polymers using thermal analysis topic, I think. And then how do you correlate molecular weight with melting peak? That is I hope I could explain that a little bit. So, what we measure in the DSC is really the crystallization or the spherulite melting. And that is indirectly correlated to molecular weight. So you know how we use nucleating agents to speed up crystallization. So if we have small molecular weight portions in our material, crystallization will happen faster. And that's also what I meant when I talked about this effect of crystallization here. Because PP is in the mixture and it crystallizes first, it creates boundaries on which LDPE starts crystallizing on. So the PP acts as nucleation agent. So it tells us the bigger the molecular weight distribution, or the shorter lower the molecular weight, the faster the crystallization happens and the higher the crystallization temperature. But it's not a straightforward method. You would need also, again, something like a calibration. You would need the molecular weight of different materials, and you would then be able to correlate that to crystallization and melting behavior. But you would have to have some knowledge of molecular weight. You can't get information of that directly. For that, again, molecular weight, there's GPC, gas permeation chromatography, that you can use, and to really directly measure molecular weight, or you use rheology, rotational rheometry, for example, to study that if you want a dual use piece of equipment.